Now we can talk about our L of k m n. I have given you an idea of how you look at the blocks and look at the determinants of these blocks. So what about L of k m comma n? The Laplacian matrix of complete bipartite graph with one side, one partition having m vertices and the other partition having n vertices. And what can we say about the spectrum of this? So first of all, we have to look at the matrix. So let us go procedurally, look at this matrix Kmn. How does it look like? So we know how bipartite graph, adjacency matrix of bipartite graph looks like, right? How does it look like? You have a 0 block followed by a j block. Here it is complete graph, so you have a 0 j and j transpose followed by 0, right? You will have a 2 by 2 block, big block if you take. So now what happens to the Laplacian? I mean, wherever you had a plus 1, there you are going to make it as minus 1, right? Nothing big, okay? So if you look at this, the Laplacian is going to be again, sorry, it's not 0. So this would be minus j mn, it's an m by n matrix. So let us look at the first m rows and n, the followed by the n rows of second partition. So this would be say minus j mn, because every edge is going to be negated here, right? And this would be nothing but j n m, or it is j m n transpose, right? And followed by the 0 matrix, right? So this is the block. Sorry, this is not 0 again. So what will be these two? Is it 0? I have said it is not 0. So what should it be? So this would be, diagonal entries should be degree, right? That we have to still keep track of. We are talking about Laplacian. So here from the first partition, you know every vertex has degree n. So this would be n times identity matrix, and this would be m times identity matrix, right? So now if I want to find the spectrum of this, I want to find the lambda eigenvalues, right? If I do usual method, if we try to do, we have to take the corresponding vector, try to multiply and see this. So the same way we will start. Suppose lambda is an eigenvalue. Here for every graph I am giving you different kind of getting the eigenvalues. So you can use any of them, whichever will fit into the context, okay. So suppose lambda is an eigenvalue of this graph, of this matrix LKMN, and so let x, y, the block vectors, let us look at it. X is of order m and y is of order n, okay. So let us look at these block vectors. So x, y is an eigenvector corresponding to this lambda. Like we proved yesterday, we had already done this exercise, right? We did for adjacency matrix. So similarly, we will try to extend and find the value of lambda, what this lambda would be now, okay. So now if I multiply this, what should I get? If I take this L matrix, multiply by this xy vector, I know this is going to satisfy lambda times xy. If lambda is an eigenvalue, corresponding eigenvector is this, then we know this equation is going to be satisfied. So if I just put all these things for this matrix specifically, what do we get? We get an equation to solve for. So we try to solve it from there and get the eigenvalues. Okay. So what would be this? If I just take L as this matrix and multiply it with this vector, what do I get? So the first block, if we look at it, it would be nx minus j mn y should be equal to lambda x, right? The first block, it would be equal. Similarly, we can see that my minus j mn transpose x, or j n m, you can write it, this would be equal to lambda y, right? So from here we can rewrite this whole expression as n minus lambda times x is j mn times y, and m minus lambda times y is j mn transpose x, right? So now let us look at this expression. M minus lambda into n minus lambda times x. What can we say about this? I want to connect these two. Literally I am doing that. I want to connect these two. How can I do that? Or in other terms, from these two equations I am trying to eliminate y. Okay. So, if I try to eliminate y, I just substitute for y this expression j mn transpose x over m minus lambda. Okay. So, this would be nothing but j mn into j mn transpose y, and what is this? Yeah, I do not have a lambda here. So, okay, let me do it step by step, so you will be able to easily understand what I am trying to say. So, look at this, n minus lambda times m minus lambda, oh sorry, I started with x, okay, that is not a problem. So, n minus lambda times this would be nothing but j m n y, right, and this would be, yeah. So, now, so this is m minus lambda times j m n y, and now for m minus lambda times y, that would be nothing but j m n into j m n transpose x, right. So, we can see that this left hand side expression, and what is this right hand side? J m n into j m n transpose Laplacian of g, j m n into j m n transpose. You have all ones matrix, a rectangular matrix, and you are taking the transpose of it and multiplying it. So, we are going to expect here that we will have obviously j m n into j n m, which is going to be of order m, right. So, we get a matrix of order m by m, and if you look at the rows, you are going to multiply every row of 1 with every column of 1, it is going to add up to n, right. So, every entry in this matrix will be having the value n. So, this is nothing but n into j m into y, right, it is all ones matrix, right, n times j m we will get because we have j m n into j m n transpose, right. So, now from, sorry, this is x. So, now from here what can we say? M minus lambda into n minus lambda is an eigenvalue of this matrix n times Jm, right, because now we have got an eigenvalue expression, right, some quantity into a vector x is equal to a matrix into the vector x, right. So, from here if you just equate these two, you see that n minus lambda into m minus lambda x is nothing but n Jm into x. So, we can see that this product is going to be an eigenvalue of n times Jm, right. So, what are the eigenvalues of n times Jm? 0 and m, right. So, and you also have an n times multiple of it, so that means 0 and nm, right. So, that means what, my n minus lambda into m minus lambda should be an element coming from either 0 or m into n, right. So, if we solve for this equation, what do we get? We will have two equations to solve. So, either lambda is equal to m or n, right. If I equate it to 0, first eigenvalue, if this product is equal to 0, then I can say lambda is n or m, right. Similarly, if we equate this n minus lambda into m minus lambda to be equal to mn, what do we get? You have to just solve this quadratic equation, right. So, if you solve this, you get the value to be equal to, so lambda would be equal to m plus n, because if you just expand the left hand side, you get lambda square plus n plus m into lambda plus mn term will be there, that gets cancelled out. So, you will just have lambda is equal to m plus n or 0, right. So, we will have lambda into lambda minus of m plus n, right. This is equal to 0. So, solving this, you get m plus 1 or 0 to be eigenvalues. So, these are the 4 eigenvalues that are possible for my Kmn, right. Now, counting the multiplicities, what would be the multiplicities? So, we will go back to our thing here. So, if m is an eigenvalue, with what multiplicity should it be occurring? The eigenvalue m can be part of this block, right, the first ni block, right. So, from there we can see that this would occur n times, and 0 occurs one time and this occurs one time. So, this will be n minus 1 times and m minus 1 times. Okay. So, this is going to be the spectrum of L of k m n, right. So, next what we will do is, we will go into another part of something that would interest you. We will digress and come back a little bit. We were talking yesterday about the largest eigenvalue and second largest eigenvalue, all those things, right. And we know if our Laplacian matrix corresponds to a connected graph, then we know there will be exactly 1 0 eigenvalue, right. So, what can we say about the second smallest eigenvalue? It is going to be positive, right. So, the second smallest eigenvalue lambda n minus 1 for any graph G, say if G is connected, this is going to be positive, right. This much we know. In fact, this quantity has a very special name in the theory. We call this as the algebraic connectivity of the graph, okay, because this kind of determines whether your graph is connected or not. So, it just tells you about this lambda n minus 1 is also called as the algebraic connectivity. And let us now look at the eigenvector of this second eigenvalue, the second smallest eigenvalue. So, what do we get, what information can we get out of this? Okay. So, if we have an eigenvector for this, say x is an eigenvector having x1, x2, xn, right. So, there is this result by Fiedler which talks about, so when we enter into network sciences and studying large scale networks, this vector plays a huge role. Okay. So, this vector is called as a Fiedler vector, which is named after the mathematician Fiedler. So, this is nothing but the eigenvector of lambda n minus 1. So, why this vector is so important is that if I give you a, suppose let us take a real number r. So, obviously we know all these vectors are going to be positive or negative, it is a real vector. So, suppose I give you a real number r, okay, and let me split, so whenever we say eigenvector, what are we trying to do here? We are assigning these values to my vertices, right, x1, x2, xn corresponds to the values that we get and we put it in for say v1, v2, vn, right. All these vector values, eigenvector values are a kind of values that we assign for the vertices here, right. That is what we are going to do with eigenvectors. So, given a graph, what we do is, if you get an eigenvector of say like, you might not get whole numbers, suppose you have like 0.25 minus 0.23 plus 57 or minus 3, something like this. If you get, what we are doing is actually we are going to assign each of these values, the vector values will be assigned to my vertices, okay, corresponding vertices. So, x1 would be assigned to the vertex 1, x2 would be assigned to this, and x3 is going to be assigned to vertex 3 and so on, right. So, by this what we are trying to connect here is, suppose I give you a real number r, okay, and I now partition this vector based on their value with respect to this r, okay, whether these values are less than r or greater than r. Okay, we can just partition it for any real number we can pick up and we can look into this partition. So, if r is any real number, let us look at the partition of the vertices such that say vi, the corresponding xi is less than or equal to r. I will take less than r and either way it does not matter. So, vi such that xi is greater than or equal to r. So if you look at this division of vertices, can you get some feeling what will happen to this? The induced subgraph of these two vertex set, if you look at it, they are going to be connected, okay, and this two vertex set clearly partitions the behavior of the network, okay. So if I am trying to look for a cluster in my network, okay, this Fiedler vector gives me the clusters, gives me all possible clusters, so that when I look into this R, I am trying to kind of collect all those vertices which are close by, right. Less than R means like they are all going to be close by together, or at least they have a common behavior pattern, right. Similarly, when they are greater than R, they all will have a similar pattern, and why do they take a positive value, like positive in the sense greater than R? Because they play a better role in the network, okay. The weight these eigenvectors give, it allows you to partition your vertices into two parts such that each of them are connected and they form a cluster among themselves, okay. So this is what Fiedler proved. So suppose we have this partition V1 and V2 as defined before, then V1 and V2 are, okay, I should just say the induced subgraph. Then the induced subgraph of V1 and V2 are connected. For any R we can take, but preferably R equal to 0 works most of the time. You can choose any R depending on, obviously we do not want to put all the vertices in one cluster. So we will usually choose between the range of the least value of the eigenvector and largest one, you can divide it. So that gives you a better partition, and usually 0 works the best. So that means like we can pick out all the eigenvector values with negative, those will form a cluster, with positive those would form a second cluster. So we could partition the vertex set into two parts. So this was proved by Fiedler in, I do not remember the year, like around 1980s I guess. So suppose the next question comes, suppose I want to find more than two clusters. Of course, the community in big networks, you do not have just two clusters, right? You are expecting to see lot of clusters here and there, right? So how do we get those clusters? Suppose I want to go for a three clustering of my nodes. So one iterative process what we could do is, so first I take the second smallest eigenvector, right, my Fiedler vector, I find the partition for that. Now on this partition vertex, now look at the behavior of the next smallest eigenvector. Just go from the lower level. We know the 0 vector always, I mean the eigenvector corresponding to 0 is going to be of equal components. So it does not distinguish any of your vertices, right. So your next second smallest vertex, second smallest eigenvalue gives you a partition, it partitions into two large clusters. Now let us go into the next level, look at the next eigenvalue and the corresponding eigenvectors, okay. So now if you look at those eigenvectors in each of these clusters, right, I mean each vertex will have a value. Now inside this you try to identify a R value which could give you a clustering of the nodes further down, okay. So this way you could repeatedly proceed and you will be able to get a number of clusters as you require, okay. So this is one beauty or the greatest application that has been found now, especially in community detections in large scale online social networks or other places also, okay. Not only social networks but also in many other large scale networks we want to find clusters, right. So in case of genetic networks we also want to find the behavior of genes, how do they react with each other and to which genes, I mean two of which genes have a closer affinity, like that. So in every network we have this kind of community detection problem. So Laplacian spectral values gives a good lead to that. Okay. Not only Laplacian spectrum, it was also proved in 1988 by Powers. This I remember, 1988. He also showed that even adjacency spectrum can be partitioned. Okay, in similar analogous way, you can try to partition the adjacency spectrum also. But Laplacian spectrum gives you a much closer, I mean the clustering is very compact with Laplacian. Say if you are looking for, when I go into the second level, I can give, say for this one cluster, so first suppose I have a cluster partitioned V1 and V2, right. When I go to the second level, for a particular value I might not partition these vertices, right. That R whatever I take, it may not partition this one of the groups, it may just partition the other class, right. So then you may have 3 clusters possible. So it depends on the value of R that we are giving, right. So usually by practice you can identify, but in large networks we usually stick to R equal to 0. So that usually gives you a better classification.